Welcome to The Explainer. Today, we're unraveling what might just be the absolute greatest identity crisis in the entire universe. We're talking about light. For centuries, brilliant minds have completely agonized over its true identity. I mean, is it a wave, just washing over the cosmos? Or is it a stream of tiny bullet-like particles? Well, let's dive into this because the answer is going to completely change how you view the reality around you. So if you go up to a physicist and ask, hey, is light a wave or a particle? The honest answer they'll give you is yes. Seriously, yes. Light actually doesn't have a definite permanent nature. It's totally bipolar, and its behavior depends entirely on the specific experiment you set up to measure it. Think about that for a second. The very act of how we observe it literally changes what it fundamentally is. Here's our game plan for today. We'll start with the wave-particle paradox, zoom into the metal surface, run through the photoelectric experiments, meet the photon, and then wrap the whole thing up with Einstein's quantum theory. All right, part 1, the wave-particle paradox. Now, it's absolutely crucial to understand right off the bat that these two natures of light, wave and particle, can never be observed at the exact same time. The battle lines are completely drawn. When you look in a mirror or you watch light bend through a glass of water, that's reflection and refraction. And those phenomena, they can only be explained by the wave theory of light. But when we look at things like the photoelectric effect or the Compton effect, wave theory just completely falls apart. Those interactions only make sense if light is acting as a distinct physical particle. It's a hard dividing line. Moving on to part 2, escaping the metal surface. To really wrap our heads around the particle nature of light, we have to look at what happens when energy physically slams into a solid object. Imagine a tiny electron trapped inside a chunk of metal. It can't just leave whenever it wants to. It basically has to pay a toll. So the key concept here is the work function. This is the minimum ransom of energy required to rip an electron out of the metal's grip. And this toll depends entirely on the specific metal you're dealing with. For example, cesium has a pretty low work function, about 2.14 electron volts. It gives up its electrons super easily. But platinum? Oh, it holds on tight. You need a hefty 5.65 electron volts of energy just to get one electron to escape. So scientists have figured out 3 main ways to pay this energy ransom and cause an electron to emit. First up is thermionic emission, which, is exactly what it sounds like. You heat the metal up until the electrons get so incredibly energetic, they literally just boil off the surface. Second is field emission, where we use an intense electric field. And third, our main suspect for today is photoelectric emission, where we use the raw power of light itself. Just to put this into perspective, in field emission, forcefully ripping an electron away requires an impossibly strong electric field. We are talking in the neighborhood of 10 to the power of 8 volts per meter. It's a total brute force method. You're essentially using a massive battery setup to physically yank those negatively charged electrons straight across a gap. Which brings us to part 3, the photoelectric experiments. Thankfully, brute force wasn't the only way. Scientific detectives soon discovered that light could do this exact same job with incredible elegance. The very first major clue came from Heinrich Hertz. He was running electricity through discharge tubes, kind of like early neon signs, and he noticed something super weird. When he shined invisible ultraviolet rays onto the negative plate of the tube, the electricity suddenly flowed way more easily. He didn't entirely know why, but he knew the light was acting like a magic switch. Then came Wilhelm Hallwachs. He took Hertz's clue and pushed it even further. He took a negatively charged zinc plate and just blasted it with UV light. Astonishingly, the plate started losing its negative charge, became totally neutral, and if he left it there long enough, it actually became positively charged. This was huge. It proved that the UV light wasn't just helping electricity flow, it was actively kicking negatively charged particles right out of the solid metal. Finally, Philipp Lenard provided the definitive proof. He set up 2 plates in a vacuum tube, a cathode and an anode. When he shined UV light on the cathode, electrons ejected, flew straight across the vacuum to the anode and created an electric current. But if he shined that exact same light on the anode, absolutely nothing happened. This proved the distinct directional flow of photoelectrons. The light was literally acting like a stream of billiard balls, knocking electrons in one specific direction. All right, part 4, meet the photon. To actually explain these bizarre billiard ball-like collisions, physics had to invent a completely new character. Say hello to the photon. A photon is a tiny, indivisible quantum, a discrete packet of energy.
and its properties are pretty mind-bending. First, they always travel at the absolute speed limit of the universe, 3 times 10 to the 8th meters per second. Second, they have absolutely no electrical charge. They glide right past magnetic and electric fields completely unaffected. And perhaps the wildest part? They have a rest mass of exactly 0. They literally only exist because they are moving.
And that leads us to our final section, Part 5, Einstein's quantum theory. So how do we actually calculate the power of something that has 0 mass and travels at the speed of light? Well, Max Planck laid the groundwork, and Einstein ran with it, establishing that the energy of a photon, E, is directly proportional to its frequency, which we represent with the Greek letter nu. So the formula is E equals h times nu, where h is Planck's constant. What you should really take away from this is quite simple. The higher the frequency of the light, like ultraviolet or X-rays, the more energy that tiny photon packet is carrying. Now, in physics, constantly converting between wavelength, frequency, and energy can get super tedious. But scientists use a brilliantly simple shortcut, the number 1240. If you know the wavelength of light in angstroms, you simply divide 1240 by that wavelength, and boom, you instantly have the photon's energy in electron volts. It's basically the ultimate physics cheat code for understanding exactly how much punch a specific color of light packs. But wait, it gets even weirder. I mentioned earlier that photons have 0 resting mass, right? But because of Einstein's famous equivalence of energy and mass, a moving photon has what we call an effective mass. And since energy is tied directly to wavelength, this means that the effective mass of a photon actually changes depending on what color of light it is. The mass is inversely proportional to the wavelength. So here is how this plays out in reality. A violet light photon has a very short wavelength compared to a red light photon. Because of that inverse relationship we just talked about, the violet photon effectively has a greater mass than the red photon. If you think of them as tiny moving particles, a beam of violet light is literally heavier and hits with way more momentum than a beam of red light. This perfectly explains why UV light can rip electrons out of a metal plate, but you could shine the brightest red light in the world at that same plate, and absolutely nothing happens. And that brings us to the edge of the quantum cliff. We started with something as completely ordinary as the light from your desk lamp, and we discovered that it operates as a shape-shifting packet of 0 mass energy that decides how it wants to behave only the moment we try to measure it. It really makes you wonder, doesn't it? If light completely changes its very nature just based on how we look at it, what else in the universe is hiding its true identity, just waiting for us to look a little closer? Thanks for joining me on this explainer, and keep questioning what you see.